Welcome to the Space for Diplomacy podcast by Spaceport Arup R, India's space policy think tank. I'm your host, Susmita Mohanty. This podcast series features conversations on far-ranging topics such as geopolitics, tech diplomacy, international cooperation, and all things space. Today, I'll be speaking with Dr. Arup Dasgupta, who's joining me for this conversation from Ahmedabad. We hope to discuss, among other things, the impact of American tech sanctions and export control on India's space program, ISRO's policy of tech independence and strategic autonomy, ISRO's cooperation with space agencies such as NASA, CNES, DLR, ESA, and JAXA. Dr. Dasgupta, welcome to the Space for Diplomacy podcast. Dr. Arup Dasgupta retired in 2005 as Deputy Director of Satellite Communications and IT Applications at Space Applications Center in Ahmedabad, which is one of the major centers of the Indian Space Research Organization, ISRO. He's now an independent consultant and an advisor to Geospatial World. He's a recipient of several national awards. Dr. Dasgupta's current interests include space policy and the convergence of space and information technologies for creating a sustainable planet. Dr. Dasgupta has a master's in electrical communications and engineering from the Indian Institute of Science in Bangalore. He's a member of several professional societies. He's a fellow of the Indian Society of Geomatics and the Institution of Electronics and Telecommunication Engineers. Dr. Dasgupta, you and your ISRO colleagues are celebrating the 50th anniversary of the Indo-American Satellite Instructional Television Experiment, affectionately known as SITE, conducted between 1st of August 1975 to 31st of July 1976. My hearty congratulations to you and the SITE fraternity. For the benefit of the listeners, SITE was an experimental satellite communications project designed jointly by NASA and ISRO to broadcast informational television programs to remote Indian villages. Dr. Dasgupta, can you share with us the social and technical objectives of SITE?
Yeah, the technical objectives essentially, this is circa when the agreement was signed. This was in 1969, late 1969. And the project really started in 1970. And the actual implementation was in 1975-76. So you have to go back to that time frame. In this time frame, the project wanted to demonstrate the possibility of using a high power satellite to directly beam television signals to a simple receiver on the ground. In fact, I would say that this was a precursor of what we now call the DTH. Okay, this was perhaps the technical part of it. The social part of it was, as you know, in India, there are a whole lot of areas which are really, even today, not covered by even the internet, right? And satellite was a very far-fetched dream in those times. But the idea was that these kind of unreached people, so to speak, could they be reached using the medium of satellite television, and then use this medium to be able to, for example, enhance children's education, school education, and also provide a kind of tertiary education to the adult population in these villages, relating to agriculture, relating to health, relating to various government schemes that are there. And so the idea was to use the satellite as a medium to do this kind of tertiary education. And this was a 1 year project, and you don't expect huge changes in that 1 year. But the point is there a rate of change? Is there a growing, realization amongst these people that yes, there is something in this for us. This is something new that we can learn, right? So this rate of change was being measured, and the unique part of this experiment was really the social research that accompanied this program. Even as the villages were selected, we had social researchers going out to the villages understanding of the village environment, understanding the villagers' needs, and then looking at how they reacted to these programs. And in the end of the day, when site closed on 31st of July 1976, they then took all their data and studied it, and they found that there was a positive impact. So this was the kind of social part of the experiment. In ISRO, we call this as the end-to-end experiment. You start with an objective, you build on the technology, you build on the other resources, and finally you go to the end result. So this is the kind of thing that we had. And
Can you share some real life stories given you were directly involved with site?
oh, there are many, but let me just tell you one or two of them. Let me give on the technical side. Uh, I'm a team of us had gone to the Goddard Space Flight Center at Washington. We carried with us the commercial part, the commercially built part of the satellite hardware, the receiving hardware. We set it up in Goddard, and at the ATS-6 satellite, which was at that time positioned over the US, we could use that, and we ran a whole lot of tests. Now, the interesting part of it is that, of course, this was the first time that we were actually connected to the satellite. So in the satellite, and we used to get time in the satellite in late nights, because in the daytime, apparently because of the rules of the game, you could not transmit that 860 megahertz signals in the US. So we used to go to work at 2 o'clock in the morning or 3 o'clock in the morning, and it was a great thing to see the signal come on first, and we got it on the spectrum analyzer, and there was a little pip. Uh, so we were elated. Then when we measured the pip, we found that the pip should not be as small as it was, because the signal was nearly 20 dB down. So next day, I got a call from Mr. Kale, who was the director, and he asked me how things were going. I said things are going fine. We got the signal, but this was the problem. So he thought for a moment and said, check on the feed. Check. Now, a little bit of technicality here. The transmission from the satellite is what is called circularly polarized. Now, you have two kind of polarization, left circular and right circular. We were supposed to use left circular. It turned out that the feed that we had got from the manufacturer was the opposite. So, therefore, the signal was coming low. Now, the interesting part is the moment I checked this out and conveyed it to Mr. Kale, that Mr. Kale immediately stopped the manufacture of the antennas and had the feed rewound. And already 300 antennas out of a total 3,000 were already made. But still, that was a 10% loss. Rest of it, they corrected it. So that was a kind of great technical gain that we had from that visit we made. There were many other stories, but let me come also now to the field experience in India. And I was, because I was in charge of the field operations, right from selection of villages to the installation of the direct reception sets, and then made their maintenance and so forth. So one of my field trips were the installation work was going on, and I think this was in Bihar. And I was there on a field trip, and suddenly there was this huge delegation from a village. Now, the problem was that the village delegation came and asked me, "You are from the headquarters, so you tell me why our village is not selected, but a village next to us, which is very poor village, do you have selected them? Now, what is this? No, we are such a advanced village, and this village is such a backward village, and you chosen the backward one. Now, how do I explain to these people that we wanted to choose only the backward villages?" So then I took a bit of a subterfuge and said, "Okay, this is all done on computers. So perhaps the computer has made a mistake. I'll go back and check out and see." So you guys are not satisfied. So I say, fine, you go, and this is all going on in the Hati Bihari, which is also adds to the flavor of the thing, but I'm not going to repeat it here. So he said, yeah, you go and tell your computer and see if it can correct it. And if it doesn't correct it, doesn't matter. You install it in that village, we will go and pick it up and install it in our village.
I think it's brilliant because it also tells you that there was such need and demand for what you, as a young group of scientists, were experimenting with. It's brilliant.
And this was an eye opener, actually. And once you go to the field, you realize all the technology that you really developed and everything else has to be acceptable at the ground level. And this I have seen all over. I mean, later on, I worked on Earth observations. The same things happened there.
So I think what you earlier mentioned about the social dimension of the Indian space program comes alive through an anecdote like this. This kind of technology is not only acceptable, it's desirable. And often they demand they have it. So I think that connects the dots for the space program that we have. Let's talk a bit about someone a little distant, not too far, but back in the day, renowned science fiction author Arthur C. Clarke, who used to reside in Colombo in Sri Lanka, was given an antenna and a site television set. How did that come about?
Yeah, that's for that I have to go back a little into history of communications. Arthur Clarke was the first person who thought of the idea of that if you put three geostationary satellites 120 degrees apart, then in effect you can communicate from anywhere in the world to anywhere in the world. And he wrote a paper on this. This appeared in a magazine called Radio Electronics, and this was way back in 1948, just after the war, and 3 years after the war ended. And Arthur Clarke was very much involved in the war. He was, I think, one of the radar operators or radar designers during the wartime. So this idea, and mind you, this is a point where you didn't even have any kind of communication satellite, not even the experimental ones. But this idea caught on. And if you really look at SITE and the ATS-6, the ATS-6 was in that particular orbit, which is now known as the Clarke orbit. And, it was actually moved to um, over East Africa. And it was pointing towards India. And that's how we were able to use that satellite for the SITE experiment. No, it was felt, and I tried to find out how it happened, but it really it was somebody's idea. Perhaps it was Professor Yashpal's idea. Professor Yashpal was our director at that time. So perhaps his idea that why not, since he's in Colombo and the signals are available in Colombo too, so why not we gift him a site receiver, and then he can see how his idea of 1948 has fructified into something like this, which actually helps the common man. So that's how it was done. Of course, Colombo was a little outside of the main reception area, so we had to give him a much bigger antenna. All that was done, and it was installed, and I think Clarke was very, very happy, and he used to take pictures of the programs that we were projecting at that time. So
I'm told that he also sort of, because of the success of the experiment and his participation in the experiment, I think I read someplace that he also sort of became an ambassador for the side project and did nudge NASA to continue the project beyond the year, beyond the allocated year. So I think it was a great move by Professor Yashpal, goodwill and sort of an ambassador friendship with us. Let's fast forward 50 years to now. NASA and ISRO successfully launched their joint mission, NISAR, on the 30th of July from Sriharikota. The fact that the launch coincided with the site anniversary surely was no coincidence. Uh, can you tell us what are the highlights of the $1.5 billion NASA ISRO collaboration, both in terms of technology development and mode of collaboration, and what are the intended outcomes of NISAR?
well, that's a long question. Let me go bit by bit. Actually, the whole idea was NASA's, because the National Academy of Sciences had pointed out the certain data gaps in the Earth observation programs. And they had suggested something called a deformation ecosystem structure and dynamics of ice using an L band L-band SAR, they had already flown on the shuttle SAR mission, and therefore they thought that they had enough experience on that kind of data processing, and they knew that the L-band SAR data was very good in terms of penetration of surface cover. So they suggested this as as a possible satellite. And India also at that time was in the process of looking for an S-band SAR system. So this was an opportunity which brought the two organizations together. There were a lot of initial discussions, and then in 2014, if I'm correct, the formal agreement was signed. And then the work was divided, and so NASA, ISRO provided the main satellite bus and the entire avionics on that. NASA provided the L-band SAR, of course, but what the L-band SAR required was a huge antenna, because you wanted to cover at higher resolution, and the bigger the SAR antenna, the more the resolution. So they had this huge antenna. I think it was some 40 feet across. So that antenna was supplied by and the L-band SAR electronics was provided by them. They also provided, I think, the high data rate transmission system. ISRO provided the S-band SAR, which used the common antenna, and ISRO provided the launch services. And ISRO is also providing the data reception services, at least over the Indian subcontinent. And other than that, the purpose why this whole thing was done was actually here also there was a meeting of uh, requirements, uh, because while the SAR is a very important instrument as a all-weather sensor, right? But at the same time, the frequency at which you are operating also makes a difference. Now, the L band, as I mentioned, it penetrates very deep. So it penetrates the vegetation, it penetrates the soil, it penetrates the snow cover. In fact, you almost reach uh, the rocky structure of the earth. Whereas the S band does not penetrate that much, but it is affected by the vegetation. So if you combine the two, what you get is you do get the details of the coverage on the earth, but also you get the vegetative cover. And therefore, what happens is then you can look at the cryosphere, you can look at the biosphere, and then you can work out large number of programs. For example, soil moisture. For example, crustal deformations. The L-band SAR can detect crustal deformations to be as low as 4 millimeters. That's something fantastic. Then of course, therefore, it's very useful for the mm, prediction of for earth, earthquakes and so forth. In fact, just we have had an earthquake in Kamchatka Peninsula, and perhaps if uh, s- Visar gets operational, that will perhaps be one of the first places that they will want to investigate. Then, of course, the other the flood the flood flood management, the earthquake management, landslides, all these come under the application. And this SAR, the satellite itself, NISAR, is going to cover the entire Earth in 12 days. So every 12 days, you will get a picture of the whole of the Earth. And mind you, because it goes through the clouds, so you get a total picture. No interference from clouds and so forth. So this is going to be a fantastic data set. And what is more important is it's open data set. It will be freely available. So no restrictions. So
I
that
mean,
is,
clearly, it was a big budget, highly sophisticated project where, from what you've told us, we are leveraging two frequencies for synthetic aperture radar to understand Earth's tectonics, the cryosphere, the vegetative cover, and also use it for disaster warning and management. So, given that it will cover the entire Earth every 12 days, will countries other than India and the US be also able to use the data from NISA for various applications?
I think so, yes. because the data is going to be open and free. So there are going to be several data archives. NASA will have its own archives. We will have our own archives. And as per the agreement, it will be openly and freely available.
Let's talk a little bit about open source satellite imagery and the power of open source. We also have a Sentinel constellation under the Copernicus program of the European Space Agency. We have the Landsat series of satellite from NASA. It's an old series that they have been, renewing periodically. What is the power of open source satellite imagery for the world?
You see, this is something that I have also felt we have kind of, missed the bus because we are using public funds for making these satellites and collecting the data. And therefore, if it's a publicly funded project, then the data should be available to the public. It's as simple as that. And in this case, I think the Copernicus program and then the Landsat program, which completely now is free to download, these are very good steps. In fact, in my opinion, in India, we missed the bus. Of course, now they say that yes, you can up to the 5 meter data, it is freely downloadable. But I say freely because our network is not so good. And so many of the remote colleges located in remote areas find it difficult to download even that kind of data. So those are other issues. But in principle, we have adopted this point that we will make the data available, but because of security reasons, we limit it to 5 meters. Okay, but still that's available.
So you're saying that, of course, there will always be security concerns for every nation, but as an expert in the field, you are a proponent of data being made available freely to, nations, to governments. If I remember correctly, I had read that the Australian government, for example, has a very well-funded program where they have used Landsat data over the years, archived it, of course, over Australia, which is relevant to them. And sort of after creating meta tags and data hygiene, they have now made that data cube for the entire country, for Australia, available to their scientists, their government departments, and what have you. So I think the power of open source is reflected in that kind of a project. Uh, um, I remember you just mentioned that the NISAR agreement was probably signed in 2014. That was, I think, President Barack Obama was in office. Why has it taken so long after the agreement was signed for NISAR to fly?
Good question. But the thing is, when you are looking at a kind of collaboration which is physically separated in two continents, right? And at the same time, you have the need to move heavy pieces of hardware back and forth, right? So, like the S-band SAR, which was developed in India, had to be taken to US for testing and integration with the L-band SAR, and then the whole thing had to be brought to India to be integrated with a satellite bus, and then the whole thing had to be tested. And during the testing, if any was found, then if the fault was on the American part of the coil, it had to be all taken back, and the fault rectified, and again bring it back. So this kind of to and fro itself took a lot of time. Further, you work across time zones, right? So when you are in India, when you are morning, your night in the US. So even conversations have to be adjusted so that could talk. When you wanted to talk, you want to talk at times when both of you are available. So these are the kind of restrictions that are there. These are physical, geographical restrictions, and this perhaps was one of the reasons why things got delayed. I do know that there was some difficulties while the testing was going on, and this kind of back and forth had to happen. But you have to work with these. in this kind of a huge, highly technical, highly complicated project. So,
And I think once India and the US have worked on such a technically complex project, it'll become probably the collaboration going forward will become even easier, having done this one time round. One of the other highlights of the NISAR launch was that it was launched on ISRO's GSLV Mach 2 rocket, as opposed to the PSLV rocket, which is traditionally used by India for launching Earth observation satellites. So, this was the first time that a GSLV, a heavy lifter, was used to place a large satellite in a SSPO orbit, which is a sun synchronous polar orbit, as opposed to the equatorial orbit. Back in the early 1990s, when Russia was planning to do a cryogenic tech transfer to ISRO, we were planning to use this cryogenic technology for the upper stage of the GSLV rocket. US imposed sanctions on ISRO and the Russian company Glavkosmos, which was going to supply that technology, claiming that the transfer would be a violation of the MTCR regime. The American sanctions forced ISRO to independently develop its cryogenic engine program. So NISAR essentially flew on a GSLV three-stage launch vehicle with an indigenously developed cryogenic upper stage. Dr. Dasgupta, how have American tech sanctions over the decades and their export control regime, ITAR, shaped India's space trajectory?
okay, so um, one of the things of the Indian space trajectory has been build yourself, but in the meanwhile, if it takes time for you to develop certain thing, buy. Okay, so there is always a build or buy option in all our projects. We start the building, and if we are successful, then what we have built flies. If we are not successful, then what we have built will not fly immediately, but will fly later. This is been our philosophy. Now, as far as sanctions are concerned, this is not something new. We got sanctioned first, I think, in 1974 itself when we had Pokhran 1. And then we got sanctioned again in 1988 when we had Pokhran 2. And then, of course, ITAR was and MTCR were always there. Right? In fact, the entire nuclear deal was subject to that ITAR and MTCR kind of rules. So we had to accept it and we had to work around. For example, I'll tell you this kind of sanctions also, because these sanctions are all basically related to dual use technology. That is technology which can be used in civilian arena as well as in the military field. So what happened was that because of this, we in ISRO were denied high performance computers. Now, at this time, we were also developing our own airborne SAR. And also, we had an agreement with ESA to receive the data from the ERS-1 and ERS-2 SAR satellites. And we had to process that data, so we had to start that also. Now, when we looked at the problems, we realized that what computers we had at that time was not enough, and that we needed high performance computers. The question was, how do we get it? There was a high performance computer in the National Center for Medium Range Weather Forecasting of the IMD in Delhi, but we were not allowed to use that. In fact, the US Embassy had a gatekeeper there, literally a gatekeeper who would be looking at what was going in and what was coming out. So that Cray computer with NCMW RF was not accessible to us. So at this time, what happened was the CDAC, Center for Development of Advanced Computing in Pune, they had come out with a computer called Param, which used a device called transputer. And they came to us and they were looking for high performance requirements. And then they came to us. And then we got together and we found that we could do it. So Param became the workhorse for the SAR data processing. In fact, as you know, in India, after we develop the software, we give it to the National Remote Sensing Center, and they use it operationally for all the data received from the Indian satellite. So ERS data was being received by them, and it was being processed on the Param. By that time, Param had also improved a lot, so they got the best Param machines, and the data processing was done on that. And meanwhile, we went on looking for other things, and then we found that we could use clusters of computers. For example, Intel computers, the high-end Intel computers, were very good to be used in clusters. In fact, we saw this in the Department of Atomic Energy, and we kind of took that forward. And we could develop clusters of high power computing using these kind of Intel based machines, which are freely available in India, right? So what happened therefore is that we did a workaround. We didn't get delayed very much, and in the end, we didn't need these high performance computers like Cray. And I don't know, I heard somewhere that Cray finally went bankrupt because, they had unsold stocks. They were hoping that in India they would sell a lot of Crays, which they couldn't. But anyway, I mean, this is just a story. I don't know the veracity of this story, but this is what happened. So the thing is, uh, no, even in civilian projects, like the National Natural Resource Information System, which I was heading, we needed computers, not very powerful computers, workstations basically, and GIS software. Now, these also came under sanction. We were not supposed to get them. So what we had to do is, because we were to buy these and then station them in different state headquarters. So we had to show the state headquarters as the final recipients of the all the computers and software are actually received in India, not by us, but by the parent company. And then we sent our people to check out what was received and give because anytime you buy something, you have to check out that what you got is what you ordered. So we did that, and then from those centers, they were sent directly to the locations where they were to be installed. Of course, we were there all the time. We were supervising the whole thing. But the point was, we did not buy those computers and software. Although the money came from us, we give the money to the concerned centers, and the centers would then pay for this thing. This is the way we worked around. But I mean, does this help at all? I don't know. If you look at the GSLV, this is, I mean, a classic example. We actually, if you see, the GSLV needed a cryo upper stage. This was well known even way back in 1990. And in 1990, they did start developing a cryogenic upper stage. Okay. But then, as I said, build or buy. So the build part of it, they said that it will be ready only by 1998. So it was felt that the JSLV would get delayed. So we got into we went up, actually, we looked at all over the world. Since we are interested in buying cryogenic technology with a transfer of technology, right? The US companies and the French companies, they quoted, but the quotes were very high. Russian quote was best. And so naturally, we chose the Russian quote, right? Which included the transfer of technology. Now, the this was in 1991, right? We signed the agreement with the Russians. In 1992, Russia got sanctioned, and they were forced to change the terms of the contract. So instead of the original three engines, they gave us seven engines as some kind of a sub. No transfer of technology, and of course, one engine which was basically a test cheat kind of a thing, for looking at how to fill the propellants, big liquid oxygen, liquid hydrogen as a test case and things like that. Okay, and then under this contract, these engines were being supplied. I think from year 2000 to 2007, they came in batches. Now the point is, once this MTCR came into effect, ISRO revived its cryo engine development program, and then this program went ahead, and even then, they could not supply the first tested engine before the year, I think 2000, right? So if you look at it, look back at it, the decision uh, start the cryo engine design in 1990 projected that you would get a workable cryo engine by 1998. Said, okay, it's too late for us, so let us buy. The build was not stopped, but buy. The buy had this rather unfortunate consequences. We ended up with 7 engines. I don't know. I think two of the satellite, two of the launches failed. Two were successful. Two were partially successful. I don't have the exact statistics in front of me, but then we got the Indian cryo stage. Now, the Indian engineers were working with the Russians for a long time, right? Even and by that time, a lot of the documentation we had already got. Okay, so perhaps this was the kind of benefit that we drew from this rather ill-fated contract. But finally, we made our engine. And what Nisar, this was the last part of the Nisar launch. 120, wow, how many minutes was that? Roughly about 1200 seconds or so. It was the that Indian cryo which got developed because of the sanctions, which could put in a Nisar into its final orbit. And that orbit was fantastic. I mean, it was well within the limit set for that launch. Okay. So this is some kind of an irony that a, a cryo stage which was developed because of the NTCR on us was finally launched in American satellite into space.
Indeed,
Okay.
indeed, it's quite the irony. Um, how would you characterize Indo-US space relationship over the past 6 decades, starting with the 1963 launch of the US-made Nike Apache sounding rocket from Tumba in Kerala?
If I look at it overall, I would say it is broadly positive cooperation. I mean, starting with that Nike Apache launch, NASA gave ISRO a whole lot of hardware for setting up the Tumba Equatorial Rocket Launching Station. Of course, because of the Cold War reasons, it was declared as a UN kind of facility, and any other country could also come and launch their sounding rockets there. Russians also came, and they not only launched the rocket, but they also helped us in developing the sounding rockets, right? So this was, and then of course, site followed, and site also it was very interesting. Apparently, at that time when the ATS 6 was under consideration, uh, Leonard Jaffe, who was, I think, the NASA applications in charge, was looking for a partner who could use this kind of technology which the ATS 6 was providing, a very high power satellite, which could be received with, say, very simple, low cost receivers. So I think they first considered Brazil, and Brazil, I think, was not interested. And then they found that India was also thinking in those kind of terms. And so Anand Fratkin was, I think, the international affairs in charge of or NASA. He said, let's talk to the Indians. And of course, Sarabhai was very keen to do this. Now, the trick, I won't say trick, but let's say the kind of movement is that NASA didn't want to go and tell India that we have something and you can use it. Right? Officially, NASA said, you have to approach us. And then we'll agree. So this was essentially because of the geopolitical situation at that time. Right? So that's how it happened that the first letter which Professor Sarabhai wrote in Fakrin said, no, 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 this is not what we want. You approach us saying that if you have such a facility. So the second letter was sent, and that's how site got started. So then the other thing is an Earth observation, I mean, we are very happy with NISA, right? But Earth observation really started way back in, I think, 1974, 75 or 76 rather, when Landsat got launched. At that time, it was ERTS 1. Now, at that time, you had to become a principal investigator, and then you would get the data from NASA for free and all that. Now, they approached ISRO, and then ISRO said, yeah, and Professor Pisharati, I think, was named as the principal investigator. The NASA was so keen that India participated in this that even before the agreement was signed, the PI agreement was signed, they sent us a whole batch of satellite data, landscape data. And then when we demonstrated that, look, we have not yet signed it, they said, oh, that's a sent by mistake. So that became known as a sent by.
I think these anecdotes uh, they just bring out the nuances of geopolitical relationships, which the mainstream media can never capture. I would say the NISAR, in a way, you're saying is now the new era, would you call it, of collaboration, that you think this will continue and we will work on more sophisticated missions with NASA going forward?
I think so, and I hope so. I mean, I would say that after SITE, this was perhaps the biggest collaboration between ISRO and NASA. I mean, of course, we had the Axiom program as well. But if you look at it from a technological point of view, and if you look at it from the long-term possibilities point of view, NISAR was perhaps the second biggest project which we did with NASA, and I do hope that this will continue. I do hope so, because it will be beneficial for both countries.
Even before ISRO collaborated with NASA on the NISA project, ISRO has collaborated with the French space agency, CNES, and the two agencies have launched two joint Earth observation satellites, Megatropics in 2011 and Saral in 2013. What were the objectives of these two joint missions, and how would you describe ISRO-CNES relationship?
Yeah, ISRO relationship is very deep and perhaps as long as it was with NASA. Professor Jacques Blamont, who was the head of who in fact set up CNES, he was a friend of Professor Sarabhai. And, he pointed out the importance of India having a space kind of program, and that's how INCOSPAR got organized. And INCOSPAR was really the start of ISRO.
That was in the early 60s in COSPAR, wasn't it?
It's yes, 60s, and that's how the whole program of the sounding rockets and emerged from there, and that's how the NASA collaboration emerged and so forth. The other thing is, we had a fantastic collaboration with CNES in our development of the liquid fueled rocket engine, because till that time we were working on solid fuel, right? The SLV and the ASLV both were totally solid fuel rockets. Liquid fuel rocket people have started working. But then we got this opportunity with CNES to be able to send our team, and they were developing a liquid fuel rocket, and our team would work side by side with them, and therefore pick up the technology. And in return, we would provide them with pressure transducers in large numbers. So it's got a kind of trade-off deal. But it was a unique kind of deal, I say, and TN Session was there who really, guided this deal through on part of ISRO. TN Session was that time, I think, the additional secretary, and Hill helping Professor Dhawan. So this went through, and that's how the Vikas engine got. And today also the Vikas engine is working, because the second stage of the GSLV, right, is actually powered by two Vikas engines. Of course, they have been upgraded, but the point is they were powered by these two Vikas engines. Vikas has been a workhorse for us way back from the PSLV itself, right? So this was a fantastic collaboration with CNES, and a very unique collaboration, but it worked. Then there are a lot of other small things, like we learned the Bhaskara satellites. Bhaskara satellites had the super Vidicon cameras. Those Vidicon tubes we bought from Thomson CSF. We also, in IS-1C, when we had the need for a special kind of mirror for the high resolution camera, the pan camera, which was at that time giving something like less than 5-meter resolution. That lens, that entire assembly of mirror assembly was developed for us in France by a French company. And then, France had launched a something called a satellite, communication satellite called Symphony, and they offered Symphony to us. for testing out on telecommunication circuits, and that was a big collaboration with CNES. So French collaboration was there, and then we come to the two satellites you mentioned, Megatropic. Megatropic was for understanding the tropical, meteorological, and climate processes. Monsoon, for example, is something very unique, and therefore, to understand the Indian monsoon, that was our interest. And there was a complement of sensors on board developed by the French, which we launched on our IRS bus from India, and data was shared. So this was the need for the megatropic, and then the Saral was again really for oceanographic studies. And in fact, at that time, we had the Paris Accord for the climate change, and Saral was one of the satellites which used two technologies. One was called, I think, the Argos, that is the oceanographic data collection, the data platform collection system, and Altica, that's an altimeter, radio altimeter, and that's why the name Saral came. And this was essentially used for the uh, oceanographic studies and looking at all the issues which are related to the climate change. So both these satellites were very important from the climate point.
Let's take a broader look at Europe. What about ISRO's cooperation with DLR, the German Space Agency, and ESA, the European Space Agency?
Oh yes, in fact, collaboration with the ESA had started even with the development flights. In fact, when their second development flight of their Ariane rocket was to be launched, they offered a free ride within certain power and weight limits to anybody who would wear satellite. The condition being, of course, if the launch was successful, you have a satellite in orbit. If the launch is not successful, you don't have a satellite in orbit. But it's a free ride, and so we also proposed a communication satellite, which we called later we called as the Ariane Passenger Payload Experiment, and the acronym was a very interesting APPLE, and so it was selected by ESA and it went up on the Ariane. It reached the geostationary transfer orbit. That was the first time we also used our own motor for the Apogee kick motor, because you need a motor to be able to circularize the orbit at that height. Of course, we had problems. One of the solar sails didn't deploy, solar panels didn't deploy, and the kick motor underperformed, so we had to use the thrusters. But we got Apple into orbit, and we used Apple for several years. So that was a very nice collaboration with ESA. Yeah, and then of course after the shuttle disaster, all our insats would go up on Ariane. So that was a continuing cooperation that we had with them. Then, as far as other European centers are concerned, of course, French I have already talked about. We had very good collaboration with the German Space Agency, DLR. And, both in ESA and DLR, we had training programs for people to go and, get trained on various aspects of the space technology and also on the application side. In fact, DLR, we also had, we carried their MOS sensor, which is oceanographic sensor, on board one of our IRS, the P series satellites. I think it was P3. Uh, it was oceanographic satellite, which of course we then built on that, and we had the ocean sats later on. But that was very interesting. In fact, there was one more payload which unfortunately was on the IRS-1E, the one and only launch which failed of the IRIS, of the PSLV series. So we lost that satellite, but that would have been also a very interesting payload. Then another thing that was there, and that was through DLR with the Hanover University, we had a very long collaboration on the characterization of the height, the stereo capability of the IRS-1C pan. If you remember the IRS-1C pan was a pointable thing, payload. So therefore, it was possible, to cover one swath, and then when you're in the next orbit, you turn back and you cover the same swath again. Now what you have is a stereo pair. Now, how good is that stereo pair? And for that, we had collaboration with Hanover University, and they had a lot of test sites in Europe, and we also built a few in India. And then this data was jointly analyzed with Hanover University and us to establish the quality of data, which is coming from the IRS ones. And later on for other satellites also, the Cartosats also over that. So these are the kind of collaborations that we had in Europe.
Um, if you look at more recent missions from this millennium, India has now a fairly comprehensive planetary exploration program. We have launched an orbiter to Mars. We have launched multiple missions to the moon. In 2009, one of the NASA instruments called the Moon Mineralogy Mapper M3, which flew on ISRO's Chandrayaan-1 moon mission, it played a very important role in the discovery of water molecules in the polar regions of the moon. Uh, to me, it seems ISRO has always chosen to lead while keeping the door ajar for international partners. What is the rationale for India's emphasis on strategic autonomy in the area of space utilization and exploration?
Look, if you look at the space exploration, is no longer a kind of one country effort, right? Yeah. So India basically looks at that and follows that principle. So if from all the payloads that are there on the satellites, Chandrayaan, we're going to have a Japanese rover on Chandrayaan 4, for example. These are the way that we have to go forward. You know, we cannot uh, depend only on our technology. We have to be in collaboration. NISAR is a typical example. And but the thing is, we need to also look at what we want to. We need to look at our own requirements, and therefore, while we are doing these programs, we always uh, welcome participation from other space agencies for this kind of scientific work.
So, what you're saying is India has to balance its internal needs with external demands and with the need for international collaboration. So, ISRO follows a unique path, balancing all of these different aspects. In 2023, India signed the US led Artemis Accords for exploration of the moon, Mars, and asteroids. And India, since the early days of our republic, has followed a policy of non alignment. Would you consider India's signing of Artemis Accords a deviation from that policy? After all, there is a Sino Russian bloc that is going to be competing with Artemis. What are your thoughts on that matter?
Well, India might have has joined the Artemis Accord, but that if required, India can also join the Sino-Russian Accord. I mean, I don't see anything. India has not ever said that we will not. And joining the Artemis is not a kind of a Boolean thing, right? If we join Artemis, you can't join. I mean, it's not going to play out like that. If we see that there is a benefit to be gained from the Sino-Russian Accord, we will definitely do that. In fact, Russia has been a very big supporter of Indian space efforts right from the early days. The design of the Aryabhatta, the launch of the Aryabhatta, launch of Bhaskara 1, Bhaskara 2. We have always been there, and I know that many cases when there has been certain difficulties, India has not stopped reaching out to Russia for advice and help. Same thing it's with NASA also. People like Professor Yashpal, they had such a wide, list of friends, both in the US, in Europe, as well as Russia. Professor Yashpal could just pick up a phone and talk to them and find out what the solution to the problem could be. I remember one case where there was a problem of a high power, power supply. If you remember in Bhaskara 1, we had a problem when the power supply arced over and then one camera was lost. So this, when we were going to do Apple, at that time also, because traveling wave tube amplifier needed a kind of a high power supply. And again, the same problem came as to whether to pot it or not pot it, right? So I remember Professor Yashpal picking up the phone, talking to his friends in Russia, talking to his friends in US. How do you people do it, right? So Russians suggested that you evacuate, you hermetically each chamber and you evacuate there, and then you will not have any problem with the workover and things like that. So
I think the mention here of Professor Yashpal, who was heading Space Application Center when you were at working for the center, is a very good one. For those of our listeners who have seen the movie Oppenheimer, um, Professor Yashpal belongs to that generation of physicists who were friends across geographical boundaries, despite geopolitical tensions between countries. And I think you just sort of recalled that aspect of sort of pan-continent friendships, no matter what the relationships were at the given time between the countries. I think we need to see more of that in the years ahead, given how polarized the world is becoming. Recently, we had Indian astronaut Shukla fly to the International Space Station as the pilot of a private mission called Axiom 4. Some of people in the industry have been wondering, why did ISRO refrain from joining the ISS program back in the 1990s?
yeah, we were offered the to join, but then at that time, if you look at 1990s, we had a lot of other important things to do. Establish a communication system, satellite-based communication system, which can connect the whole country together. Uh, Development of Earth observation systems, which would help in, for example, crop forecasting, forest management, and you need money for all these. And India was never, in that sense, such a rich country that one could afford to take up lots and lots of projects. I guess the situation was that one had to do a prioritization, and perhaps a manned space program was not on the cards at that time in the 90s. So the thrust was more on space applications for the Indian people, so to speak. So we didn't join for that reason. But now we seem to have come to a point where we would like to get into the manned mission for various reasons, various geopolitical reasons as well. So now the time has come, and that's why we have the Achievement mission. And perhaps we have more of, we have a Gaganyaan program now, which we never even thought of in those 90s.
So again, it's a question of priorities and timing. You just mentioned the LUPEX mission that's going to come up, which will be a collaboration between ISRO and JAXA, the Japanese Space Agency, where JAXA will be responsible for building the lunar rover and ISRO will build the lunar lander. Do you think technology is the new currency for diplomacy?
Yes, absolutely. I mean, collaboration on technology is what is something that one has to look at.
And finally, Dr. Dasgupta, I have a crystal ball question for you. What will the moon look like, geopolitically speaking, in 2050? Will it be a domain of collaboration, competition, or conflict?
It's a very deep question to answer. Yeah, I would rather say, I would take two scenarios, right? Let's take the scenario of the collaboration part. Uh, if you look at Artemis Accord, it really talks in terms of collaboration, and that is something that gives me great hope. I'm sure the Sino-Russian Accord also is going to talk of the same kind of collaboration, right? Why you have two accords is because of the geopolitical situation, right? And this is something unfortunate that we have, after so many years, we still haven't been able to overcome this. In fact, I would really, this is my personal view, but I would like to see India in both. Okay. And as far as the moon is concerned, moon is going to be the stepping stone to all other uh, planets and so forth. And also the therefore there is a need for going to the moon. And that's where I think the Gaganyaan program is important, because ultimately it has to come back. Now, why do I think so? If you look at on the Earth, the Antarctica, right? The Antarctica is not belonging to any country, but countries are allowed to put their stations there and do scientific research. Because the Antarctica award is going to come up for renewal. I don't know what will happen then. But if you look at Antarctica as a continent, no one owns it, right? But everyone who wants has a station over there to do scientific research, which also perhaps also includes looking for the kind of minerals and so forth which are there under the cover of the snow and ice. The moon is also like that, right? It's a virgin territory. It belongs to no one. As per the Outer Space Treaty, it belongs to no one, and therefore uh, any country can go and establish a station there for doing further scientific research, and definitely it will include uh, commercialization of its resources. If I look at the Artemis Accord, it addresses that. It tries to be within the bounds of the Outer Space Treaty. But I think the Outer Space Treaty has run its course, and it has to be revised and revised extensively because of the possibilities that are there. Right. So my, feel good uh, prediction is that moon will become something like Antarctica, with the outer space treaty modified to adjust the new situation. My other scenario, which is the doomsday scenario, is that there is going to be a kind of competitive, and competitive and therefore conflicting a on moon. Very much, I would say that, the way the colonial people kind of robbed the colonies of their wealth, to fight to make their own um, life very comfortable, right? And left the colonies in a very poor state. I am afraid that similar thing might happen when the people, like Elon Musk is talking of not the moon, he's talking of Mars. Okay. But what is he going to do? I mean, is he going to set up a colony on Mars? I mean, will he start owning a part of Mars? What cost? Right? So it goes right against the outer space treaty. So that can also happen. But that is worrisome, because there is historical evidence of this kind of thing happening on Earth itself.
Indeed, indeed.
People coming to colonies to gather wealth and things like that, right? Leaving the colonies completely shattered and completely losing their control over their riches and so forth. So this I have these kind of two things, and I do hope that the first one, which is more of a cooperation, and they will happen by 2050. I hope that kind of situation will be there.
Thank you. Thank you, Dr. Dasgupta, for taking the time.
Thank you very much for this opportunity. It was interesting, and I really loved chatting.
Thanks a lot. Thank you all for listening. Stay tuned for our next episode. Refer to our website, spaceportsarabhai.org, for more discussions, debates, dialogues, an explainer series, the new Space India podcast, and a newsletter about the progress of India's space program.